Welcome to this second video in the series Electrics for Heating Engineers. In this section we will go through some simple fault finding techniques. So fault finding. When a circuit doesn't work as expected, we need to find out why. To do this we need some basic test equipment, a 2-pole tester or a multimeter. A volt stick or neon screwdriver is not a suitable test instrument and in some cases are actually dangerous, so don't use them. 2-pole tester can be used to measure continuity and voltage. It will usually have an audio indication and a visual LED indicator. Some models also have an LCD readout of the voltage, and they will normally measure from 12 volts up to 250 volts, either DC or AC. A multimeter can measure voltage, both AC and DC, current, also AC and DC, and resistance. Some models have special setting for continuity which has an audible buzzer. More specialist multimeters can also measure capacitance, test diodes and resistors, etc. Some are also ranging. In other words, you put it on volts and it would automatically select the correct range. If not, always start with the highest range and work your way down so that you don't damage the instrument. Some of the terminology we'll be using. Live testing. Live testing is carried out with power applied to the circuit, usually voltage or current measurement. Dead testing. This is testing carried out with no power applied to the circuit. If we test for resistance or continuity, we always do this without power. Continuity means a very low resistance or short circuit, such as you find across a fuse that's okay or a wire from one end to the other. Safe isolation. This means ensuring that the power is isolated from the circuit or equipment you're working on and is vitally important. LV. This is low voltage. It's a bit of a misnomer because low voltage is actually anywhere from 50 to 1000 volts and this can kill you. ELV, extra low voltage. This is anywhere below 50 volts AC or 120 volts DC and is a lot safer to work on. So one of the first tests we need to be able to do is to test continuity, such as a fuse, a switch or any other component. We remove it from the circuit and we place our test probes on either end of the component. Depending which sort of test we're using, it will either bleep or it will give us a reading of 0 ohms. In this instance, our fuse is broken, so there's no continuity, and if we're using a multimeter we'll get a reading of 1, or we won't get any bleep if we're using an audible tester. So we come on to testing simple circuits. You may remember this circuit from the first module. In this circuit our lamp should light. We can see it's not lighting, so we need to find out why not. First step we'd take is to test the voltage across the battery between points A and B here. If we've got 9 volts there, then we know our battery is good. If we haven't got any volts there, then we've got a faulty battery. Fairly simple fix. So if our battery was good, the next place we would tend to check would be across the lamp at E and F. If we've got 9 volts there, then it's a pretty good bet that it's the lamp itself that's faulty. If there's no voltage there, then we've got a fault somewhere else, so we have to investigate further. So on this circuit, the first place we'd test is between A, which is the negative side of the battery, and C, the input to the switch. If we've got 9 volts here, it proves that the wiring from the positive side of the battery at B up to the switch is good. If we didn't have any voltage there, we'd have a wiring fault between our battery and our switch. So assuming everything was good so far, we'd then test on the output of the switch. So if we've got 9 volts here at D, that proves that the switch is also good. Again, if we had a lack of voltage there, then that would suggest that our switch was faulty. So the next place we check is between the negative side of the battery and the lamp, positive side of the lamp at E. If we've got 9 volts there, that suggests that everything from the battery up to the lamp is good, and it's probably a lamp that's faulty. The next step we'd test is on the negative side of the lamp. If we've got a positive voltage on the negative side of the lamp, then that suggests that our fault lies between A and F, because there's no negative return for the lamp. And this is all explained here in this flowchart. So we start at the beginning, our lamp's not lighting, so we test for 9 volts between A and B. If we haven't got it, we replace the battery. If we haven't got it, we test the lamp. If we've got volts there, replace the lamp. If not, carry on through all the other tests, step by step, and we'll find the fault. If we've got a more complex circuit, we can speed up the testing procedure. So in this circuit, we've got a battery, 4 switches, 1, 2, 3, and 4, and a lamp. So having already tested the battery, and we've tested the lamp and we got voltage at our battery, no voltage at our lamp, we can test approximately half the circuit in one go. So if we've got 9 volts between A and F, it proves that switches 1 and 2 and the wiring between them is good. If we didn't have voltage at F, we could test at E on the input to that switch, and that would prove whether switch 1 and the wiring up to E was good. Assuming that we were good at F, we've proved switch 1 and 2 and the wiring between them. The next step, we could test at I. If we don't have voltage at I, then we know the fault is between F and I, and we can investigate further. Our next step would be to test from the negative side of the battery to the input to the lamp at K. If we've got 9 volts here, that proves everything between the battery and the lamp is good. A lack of voltage at K would indicate a fault with switch 4, where our wiring J to K. Our final test would be at point L on the lamp. 9 volts here proves the lamp, switches, and all wiring from B to K is good. And in this case, our fault must be the wire between A and L. So as you can see, we can break down testing into chunks. We get a good half and a bad half. Once we know which is our bad half, we break that down into a chunk and test, and so on, and keep breaking down by half each time till we find the faulty component. This is quite often quicker than testing everything in sequence. So to summarize, testing complex circuits can be speeded up by testing half the circuit to isolate the fault to one half of the other, then testing half the section, and so on until we identify the location of the fault. Safe isolation. Before working on any low voltage, i.e. mains installation or equipment, we need to make sure the circuit is dead. Do not assume that it's dead just because you've switched off the fuse spur. Sometimes things aren't wired correctly and they get voltages coming from all sorts of weird and wonderful places. So the first step is to test your test instrument, whether it's a multimeter or the 2-prong tester. Put it on a known supply and make sure it's working. Step 2, switch off at the fuse spur or remove the 3-pin plug. Test between live and neutral. Assuming you've got no voltage between live and neutral, the next step would be to test between live and earth. And the last one would be to test between neutral and earth. If we're working on a boiler, we would then test between the switch live and neutral and the pump live and neutral just in case there's a stray voltage introduced from somewhere else that could do us harm. And the last thing we do is to test our instrument again on a known supply to make sure it's still working and hasn't failed halfway through our test, giving us false results. And then once we've made sure that the circuit is safe, make sure the supply is physically prevented from being switched on by a third party while you're working. Take the fuse out, put a cable tied through the fuse holder, or physically remove the 13 amp plug from the cable. And here is a flow chart that goes through the safe isolation process again. So from the start, test our instrument. If our instrument's not working, get another one, start again. Switch off the supply, move the plug, remove the fuse. Test between live and neutral, test between live and earth, test between neutral and earth, test the instrument, lock off the supply. Safe to work. Checking the supply. First place to start with any fault finding is your supply. Now, by necessity, this is a test that needs to be carried out on a live circuit, so take care. When we're fault finding on a heating circuit or boiler, the first thing we would check is the supply from the fuse spur. Then we would check the supply at the boiler end, assuming the boiler does have a permanent live supply. Most modern boilers do, but some of the old ones only had a switch live, so you wouldn't have any live there unless you've got a call for heat. The procedure is the same for both ends. While a lot of equipment is not polarity sensitive, in other words, it doesn't matter which way around the live and neutral are, like a light bulb, they'll still work. Modern boilers are polarity sensitive, so it's important that we check the polarity of the supply. So checking the supply, the first step is to check the outlet of the fuse spur. Test for 230 volts between live and neutral. We should have 230. If not, check the input of the fuse spur. If the input's good, test the continuity of the fuse, because it may be a dodgy fuse, blown fuse. Step 2, test between the live and earth. We should have 230 volts. Step 3, we test between neutral and earth. We shouldn't have any voltage there. If we've got 230 volts on neutral and earth, this indicates reverse polarity. Do note that sometimes you can get a small voltage depending on the earthing arrangements. It's normally less than 10 volts, that's nothing to worry about. But if you've got a significant voltage there, you've got a problem. So investigate. This slide shows you the possibilities that you can get when checking your polarity. So as you can see, live, neutral, live, earth, 230 volts, and nothing between neutral and earth is correct. Anything else indicates some sort of fault, and that could be reverse polarity, a broken neutral, no live, or no earth. And again, we've got a flow chart to go through to make it easy. So at the start, we test our instrument, assuming our instrument's working, test between 230 volts between live and neutral. If we haven't got it, then we would investigate why. So if we've got no voltage at the output of the fuse spur, we test the input of the fuse spur. Assuming the input's good, we check the fuse. If the fuse is good, then it's probably a faulty switch on the fuse spur. If the fuse wasn't good, we replace the fuse. And we could just go through the flow chart until we get to the end. So, a summary of what we learned in this module. We've learned what test equipment we need. We've learned how to test a simple circuit to find a fault. We've learned how to speed up testing on more complex circuits by breaking it down into chunks. We've learned safe isolation, make sure we don't kill ourselves, and polarity testing of the main supply, making sure that live is actually live and neutral is actually neutral. Thank you for watching. In the next module, we'll go over testing actual heating circuits.